Yeah, I need to go through the theory so that you'll understand what's going on. Otherwise, it look like very mysterious to you if I try to solve the problem directly. Okay, so what we'll do here is I will show you how the method works for 2 points, 3 points, and then you'll see a pattern emerge from those calculations, and we'll use that pattern to generalize to n points. So the problem remains the same. Fit a curve through n plus 1 data points, x0, f of x0, x1, f of x1, and so on till xn, f of xn. So here's what we'll do. We are going to build intuition for the formula starting with 2 points to fit, then 3, and so on, and generalize to n plus 1 points. Okay, let's say that we are given data for just 2 points. Okay, and that data is clearly x0, f of x0, x1, f of x1. Okay, now if there are 2 points and we need to fit a curve through those 2 points, we know the answer is just a line, right? So we'll assume this equation for f of x. Okay, now normally what you'll do is you'll assume it to be c0 plus c1x, like you would do for 2 points, y equals mx plus c. But we're going to choose it in a slightly different way. We're going to say it's c0 plus c1 x minus x0. Okay, it still is a polynomial of order 1 or a straight line, just that we have that x minus x0. Okay, now this passes through 2 points, right? x0 and x1. So we can sub in the value for f of x0. So c0 plus c1, x1 minus x0. No, x0 minus x0. Okay, this is 0. And immediately we have c0 is f of x0. Okay. Next, we sub in the value for x1, c0 plus c1, x1 minus x0. Now I can sub in the value for c0. It is f of x0, c1. Right, this one came from here. Okay, now we are left with a single unknown c1. We'll solve for c1. We already solved for c0. It's just f of x0. So solve for c1. Okay, that shouldn't come out as a surprise to you if you remember what is the slope of 2 points, right? It's just that formula. It's the difference in the y coordinate divided by the difference in the x coordinate. So with that, we have essentially solved for the constants, and hence we have solved for the equation of this straight line. So let me put that formula down, because I'll be using it for the next part. So let's get that done. So I'm going to take in the value of C0 and C1 and put it in this equation and write down an expression for f of x. Okay, how about we write this in this fashion? Plus, I'll call this uppercase F x1, x0. Okay, I'm specifically writing it that way because we'll see that the uppercase F is going to help us develop that formula. So this term here is the same as this. This is the way I will denote the capital F with arguments x1, x0. So let's box this. Okay, so we've got the equation for 2 points. Let's go on and do 3 points. Okay, what we're given here is the following data. Okay, 3 data points, and now we need to come up with a equation for f of x, and we know that if you want f of x to pass through 3 points, we should have 3 constants, which means it should be at least of order 2, right? Because the order 2 equation or quadratic equation has 3 constants. So there's a special way in which I write this equation. It is like this: c0 plus c1 x minus x0. Okay, note this was the first point. Okay, I need c2 because it needs to be quadratic. And then I'm going to put x minus x0, x minus x1. Just notice how I came up with the expression. Normally, I would write for a polynomial c0 plus c1x plus c2x squared. But in this case, I specifically want to put it as x minus x0 and x minus x0, x minus x1. Okay, you'll see why that's very important. Now we'll substitute the value for x0. So x equals x0. And here's the interesting thing. You'll see that the second and third terms are actually 0. The second term is 0 here, and it's 0 here. So what we've obtained is c0 equals f of x0. Okay. Turns out that it's the same value we had obtained earlier for 2 points. Doesn't change. You can check it with the previous answer. Next, we'll put x equals x1. We have c0 plus c1, x1 minus x0 plus c2, x1 minus x0, x1 minus x1. Okay, what happens here is this term is 0, right? And then if you try to solve for c1, you end up with f of x1 minus f of x0, x1 with x0, which I obtained by subbing in the value for c0. c0 is here. So I can put that, move it around. So if you notice carefully, this c1, this value for c1 is exactly the same value we obtained here for c1. Same thing. So what's happening here is when we add a data point to this, the 2 constants don't change, they remain the same. And we actually came up with a formula for this. We're going to write this as f x1 x0. Okay, so we found c0 and c1 is the same. Let's compute c2. We substituted x0, we substituted x1. Let's substitute x equals x2 now. So C0 is f of x0 plus C1 is f of x1, f of x0, x1 minus x0 plus C2 x minus, sorry, x2 minus x0, x2 minus x1. So solve for C2. Okay, now this solving for C2 requires a little bit of moving things around, and I'll just skip that. I'll just write the answer I got. So C2 is, it actually can be rewritten sort of by moving things around, a little bit of work, but comes out to be something like this. Minus x1 minus the whole thing divided by So notice the pattern here. This looks very much similar to what we had for C1. If you go to C1, you saw it's f of x1 minus f of x0 divided by x1 minus x0. Here we have f of x2 minus f of x1 divided by x2 minus x1. We also see this pattern here. You look at this one, that's also similar, f of x1. In fact, it's actually C1. So remember, we created a notation. We said that we'll write this term in pink as f x2 x1 minus f x1 x0 divided by x2 minus x0. But that term here, the C2, looks a lot similar to what we have for what we have over here, right? Here we have f, or lowercase f has one argument x2, right? Here uppercase f has two arguments, but the form is the same. We have x2 x0 sort of. So what we'll do is we will actually use the same notation to write this down. We'll write it as f x2 x1 x0. Now it has three arguments. Okay, now I could just keep going on, but what we notice is the following, which is choose a different, let's choose. Okay, so here's what I want you to notice. If you go back, just to get this is C0. This is C1. Well, let me. Let's just do 3 data points. Okay, this is C0. This is C1. It's f uppercase f x1 x0. If you go to C2, it's right here. It's uppercase f x2 x1 x0. Okay, so only first one C0 was lowercase f, C1 was uppercase f with arguments x1 x0, C2 is uppercase f with our three arguments, and we could show this, okay, 4 points, that if you do C3, it will be uppercase f x3 x2 x1 x0, okay, where this uppercase f x3 x2 x1 x0 would look something like this: x3 x2 x1 minus x2 x1 x0 divided by x3 minus x0. Okay, so you could do this for C3, you could do this for C4, C phi, C, doesn't really matter. So basically, we've got a formula without actually doing much work. We've sort of seen a pattern, and that pattern just keeps going on. So if you want to do this for Cn, it will be F xn n minus 1, so on, x1 minus F. And what, first let me write this down, Fx0, which is going to be xn minus 1, so on till x1. We stop there, and then minus F x minus 1, x minus 2, so on, x0 divided by xn. So that's the last one. Okay, so remember why we are doing all this. Eventually, we have an equation for f of x, which goes as c0 plus c1 x minus x0 and so on. So the equation will look like this. F of x0, this is the first constant, c0, plus x minus x0, uppercase x, x1, x0, plus x minus x0, x minus x1, out of space, x2, x1, x0, and then it just keeps going till we end up with x minus x0, x minus x1, so on till x minus xn minus 1, f x n x n minus 1, so on till. So everything here is a formula we've already derived. So we really don't need to do any back substitutions. So back substitutions have already been done. What I mean by back substitution is when we did it for polynomial and Lagrange interpolation, we basically had constants a0, a1, or b0, b1, and so on. Those have been already solved for. That's all embedded in that uppercase f. We just need to know how to compute that uppercase f, and we're done. Now we're going to make a simplification, which will make our life much, much easier. What we'll assume is that when you give this data, normally data is equispaced. That is, you usually collect data at every so many after so much time, but the time interval is fixed. So every dt or whatever that is, if it is not every time every dt seconds or dt could be days or whatever, then you'd have to keep the complexity of the formula like this and use this to solve for the problem. But if the dx is constant, then this formula simplifies further. So let's do that, because most of the problems in this course will be doing that. So this is going to be a simplification for uniformly spaced points. What it means is xi is x0 plus I delta x, where I equals 1, 2, 3, so on till n. So data is spread equally. So C0 is f of x 0. C1, we wrote down the formula, f of x1 minus f of x0 divided by x1 minus x0. Turns out that we can write this as essentially delta f represents the change in x. Okay, it's basically the forward difference, what we've seen for in the differentiation part of the course. Then we have, this is f x1 x0 minus, sorry, x2 x1 x1 x0 x2 minus x0. So if you, it turns out that if you sub that value in terms of lowercase f, you end up getting f of x2 minus twice f of x1 plus f of x0 divided by 2 delta x square. Okay, so I'm going to simplify this. This is essentially the forward difference formula, delta x square f of x0 divided by 2 factorial delta x square. So we've obtained what we've got for the differentiation part of the course. And you can keep doing that till you end up with Cn. Remember that formula was xn, xn minus 1, so on, x1, x0. It's nothing but the nth derivative, which is finite difference, n factorial f0 divided by armed with all this, we have what is known as it's called a Newton-Gregory forward interpolation formula because it uses forward difference. And then there's something called a Newton-Gregory backward interpolation formula, which instead of starting from x0, so everything here was x0, you could start from back, xn, and go backwards. In that case, it's called a backward interpolation formula. So I'll write down those formulas down, and then I'll do a problem which will make it, it'll help you to understand how this goes. It's much simpler than what it looks in the formula. There's a sort of a trick to do this by hand very easily. You don't really have to use these formulas. Okay, I'll show you how that is done. But let me write those formulas down and then we'll solve the problem. Okay, so here is how these equations will look. So first we have the Newton Gregory forward interpolation. It goes as follows: plus x minus x0 2 factorial x minus x0, x0 minus x0 plus, sorry, minus delta x, so on. So until x minus, sorry, this should be x0 minus delta x. Let me just put that. It's the formula you'll see. We don't really use the formula. We'll just use a trick. But this is how it look. So Newton backward rotation. Okay, it's the same formula written slightly differently. Okay, the change being that use the backward difference. This will be xn, this will be xn, this will be xn. xn should be n. Okay. Okay, don't worry too much about the formula. You don't have to really memorize or write it down even in your exam. I'll show you a trick to do it. So with that, let's solve a problem which will illustrate how to use this. Okay, so here's how we'll do it without actually referring to the formula. We'll make a table. So for part A, so let's make a table for x. So we have 0, 1, and 2. We have y. So it's going to be 2, 0, 4. I have another point. Oh, I added another point. Hold on. Yes, I added another point to the 0, 1, 2, 3, and 2, 0, 4, and 20. Okay, the reason for the addition is because we can do much more with this because we don't really have to do any kind of tedious calculations, as you'll see. And this will help us illustrate this. So 2 and then 3 is 20. So this is how you would compute delta f. By the way, this is also same as f. Okay, ready? So what you do is, in order to compute delta f, you have to subtract the adjoining neighboring values. So in this case, we do 0 minus 2. The 0 comes from here, the 2 comes from here, which is minus 2. Then you do 4 minus 0, which is 4. And then 20 minus 4 is 16. Now, when you find delta f square, it's the same thing, but repeated with delta f. You need the finite difference over this delta f. So now what we'll do is the same thing. We do this 4 minus 2. Then we have 16 minus 4. So 4 plus 2 is 6. 16 minus 4 is 12. And then delta cube f, the same thing. You do finite difference in the previous column. So 12 minus 6, 6. Okay, now what we do is next, which is we're almost there. Now, when we try to write the formula, remember it was, if you go back, it was always the first value, delta f0, delta square f0. The first value sits right here. So this is delta f0. Sorry, this is f0. This is delta f0. This is delta square f0. And this is delta cube f0. So here's the formula. It's y equals, or f of x equals f of x0, that's 2, plus minus 2 divided by what will be here is delta x, which is just 1, right? Delta x is the difference between 1 and 0, which is 1, times x minus x0, which is 0, the first value, plus 6. This is the next one, delta square. This will be delta x square, which will be 1 square, times x minus x0, so it will be 0, times x minus x1. So x1 here is 1. And then finally, we have the 6 times x minus x0, x minus x1, which is 1, x minus x2, which is 2. And I think I forgot 2 factorial here, my bad. 2 factorial will be here, and then this will be 3 factorial delta x cube, which is really 1 cube. Okay, so to summarize, this 2 came from here, this minus 2 came from here, this 6 came from here, and then what is left over, this 6 went over here. Okay, so you really don't need the formula, right? It's just sitting right there. So now when you let me simplify this. So we need to still simplify this and write the formula in terms of x squared and x cube and so on. So if you simplify this, you get f of x equals 2 minus 2, see 2 minus x. Then we have 6 divided by 2 is 3. So 3 times x, x minus 1. And then we have 6 times 3 factorial is 6. So 6 cancels. So we have x minus 1, x minus 2, 2 minus 2x plus 3x squared minus 3x plus x cubed minus 3x squared plus 2x. So if you simplify this, you get x cubed minus 3x plus 2. Okay, that's the answer. Okay, so this is how you do Newton's Gregory forward difference. Okay, now let's do the backward one. The backward formula, okay, uses a similar recipe. It's exactly the same, except the way you, which value you use will change. So let's see how to do this. So so Newton-Gregory backward formula. So we write x 0, 1, 2, 3. We'll write f of x, or just write f. So those values were given as 2, 0, 4, and 20. Now we need the backward difference. So for the forward difference, you started on the top and worked your way down, but now we'll start from the bottom and work our way up. What I mean by that is, for the first point, I do 20 minus 4, this 20 minus this 4, so 16. Then 4 minus 0, 4. 0 minus 2 is minus 2, and then nothing on there. Then delta square f, we again start from bottom. 16 minus 4 is 12. Next is 4. Minus of minus 2 is 6. And then finally, delta cube f would be 12 minus 6 is 6. Okay, now we're done with that. Let's write down the formula for y as a function of x using Newton-Gregory backward interpolation. Okay, so how does that formula look like? If you go back here, you'll see that this formula will use the last value, xn, everywhere, right? So we need to start with the bottom value. So let's go here and choose the bottom value. So f of x would be, we need to use this, 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 and this. So first is f of x. plus 16 divided by delta x, which is just 1, x minus, now x minus xn, n happens to be 3. So this will be 3 plus this 12 divided by 2 factorial delta x square, which is just 1 square, x minus xn minus the next term, which is 2. Okay, I need to continue this, plus 6. 6 divided by 6, 3 factorial delta x cube, which is pretty much 1. And then we have x minus xn minus 1, so 2, x minus 1. So this 20 comes from here, this 16 comes from here, this 12 comes from here, and then this 6 is this 6. So let's simplify this. 20 plus 16x minus 3 plus 6 times x minus 3, x minus 2 plus so this 3 factorial is 6, so 1, x minus 3, x minus 2, x minus 1. Okay, you can try to, well, simplify this. I'm running out of time, so I'll not simplify this here at this moment, but it's fairly straightforward to expand that out, right? And when you expand it out, what you'll find is that the answer comes out to be f of x is x cubed minus 3x plus 2. Okay. If you look at this answer for part B and you compare it against part 1, it's exactly the same. X cubed minus 3x plus 2. X cubed minus 3x plus 2. Okay, so both those formulas, Newton forward or backward, gave the same answer. So the final step, part C, is figure out the value of f of x at x equals 0.5. So f at 0.5, since you got the same value, it just doesn't matter which one you use. So it'd be 0.5 cubed minus 3 times 0.5 plus 2, 0.625.